Hello, my name is Jonathan Austin, and this is one of the tutorial videos that kind of will help you, who is most likely a new member, get around and navigate this more complex project, and also kind of get a little bit of an idea of what I did in my senior project semester, which was finished in December of 2021. So you're probably here because you're interested or participating in the embedded systems part of the project, which mostly revolves around the DSP controller. And I'm going to use this video to kind of show you around with, like I said, with some of the work that I did, and also try to give you an idea of how to navigate and start out trying to hop into embedded systems for this project. Also want to thank Professor Bodaway, and it's definitely an interesting project, and really appreciate all the resources that he provided. So obviously, if you're watching this video, you probably found it where I believe I'll upload it, which is to my YouTube channel right here. And if it's ever lost, you can just navigate your way back here, but it should be linked probably in my folder in the Google Drive, and also in a guide that I'm going to show you in a second. So the first thing you should probably go navigate to is the guide for new members under Sarika's, who is one of the master students that I worked with throughout this project. Also in the embedded systems portion, we spent most of the time together in this development over this past year. So this is the guide. And first thing that you should prioritize and getting access to is obviously the Google Drive, which you most likely already have access to. And if you don't, just email Professor Bodaway. And then the next thing you should want to look into is Code Composer Studio, which is just an editor that is what you will be able to use to upload and flash code to the DSP controller in person. Then next thing would be GitLab, which I wouldn't say is super necessary, but it is necessary in the sense that you need it to get the most recent version of the code. But I wouldn't say you're most likely not going to be using it regularly, just because you'll just need to push code once in a while maybe, and that's about it. Next thing would be getting access to the GitLab repo, which is how you would get the most recent version of the code. And if you're not familiar with Git, there's a Git guide here for you to look at. Then, once you have that done, there are some introduction videos here, like this one, which is not currently linked yet. And there's also a video by Sarika and a couple of other people who did prior work that are in embedded systems or are related to it in some form or fashion. Yeah, so like I said before, this guide is going to be located here. It might get moved, but just go ahead and either look in my individual folder or Sarika's to find this. This is a good way to get started because it's definitely a complex project, and there can be a lot of things that can be a little overwhelming, so it's good to start with something that's pretty straightforward, just a list of things to do. So moving forward, something else you'll want to have access to on top of what was listed there is getting access to the Slack channel, which is essentially just the mode in which people communicate on for this project for the majority of us. And there's different channels. Obviously, if you're embedded systems, you're going to want to pay attention to this one, etc. So this has been pretty much roughly what I've been working inside of for this past year, these past 2 semesters, and it's reflected in my individual folder in the Google Drive. So first off, this took a majority of my time. This was developing an initial test for an algorithm that we were trying to implement. I'll go into more in depth in this later in the video. And then next up, this is going to be the main code, which, like I said before, you would get from your GitLab repo that you'd have access to. And then, so just for background, this is going to be the main code that is uploaded on the DSP controller. And this is ultimately what sends out PWM signals, which I'll talk about a little bit later too, to all of the different hardware levels, which I'll talk about later too. So next up, this is just some schematic and board files for the MMC DSP interface. So what I'm talking about for this is this photo here. There's a little board that is below the DSP, which is this vertical piece that has different signals that are attached to the DSP controller that you'll need to measure if you're to ever test the PWMs. And those schematic and board files just show you which of those signals are, like I kind of highlighted right here. And then next up, these are the papers that pretty much most of, if not all, the work in this project has been based off of. These are IEEE papers that Bodaway has published and updated. So you can either find these PDF papers here, or I've also linked them in our final report references section. You just have to sign into your SJSU account to access those in case those ever change. But at this moment in December 2021, those are what the papers are updated to be. Next up, we have reports and presentations. So this is anything that is relevant to our project over the course of these 2 semesters, so EE 198A and B. But the thing that you're mostly going to want to focus on, even though some of these other things might help you a little bit in figuring some of the assignments out, is going to be this final project report presentation. So this is organized. Oh yeah, so Andrew and Jerome are the other 2 people that were on my senior project group, except they worked on the power module design, so they're not going to be working or referring to anything really embedded systems wise. An executive summary, you have a table of contents here where you'll be able to find it pretty well organized. This is, if most likely you're going to be in the embedded systems portion, this is what you'd probably want to just look over just to get a sense of everything, because it gives background, it also summarizes and talks about some of the work that Sarika and I did. But yeah, these are the references at the bottom that I mentioned before with Bodaway's papers. Like I said, it's definitely a good idea to try to understand these, at least at a high level, so that we have good enough context going into the project. And then lastly, there is the symposium poster, which is what you will end up having by the end of your 198B class, which you'll present, or just stand by and then also present if somebody asks at the symposium. And similarly to the presentation I'll show you in a second, it just kind of goes over at a high level what work was done and what the project actually is. And then here's some other resources that might be important for you depending on what part of the project you're carrying on. Maybe it's the stuff that I left on. So some of the stuff that I left on is kind of more research-based in terms of trying to understand and look at how we can implement some more of these simulation things that prior members did. So like, for example, Sam worked on SOC estimation, or state of charge estimation, and what he has here are some MATLAB simulations, which are ultimately really helpful for understanding how the estimation works, because it utilizes something called the Kalman filter, and this is ultimately what we want implemented in the main code. But it was definitely took a lot of time to understand it, so it would just be something else for another member to carry on. These are some videos kind of going over that and some other things. So keep in mind all of these file pathways inside of the Google Drive. So Sam, Sarika, tutorial videos. And then finally, this is the simple model, in which encapsulates pretty much the majority functionality of the entire system, which would be essentially this block diagram right here. So this, especially if you're into MATLAB simulations, this would be something good to take a look at. This was done by somebody named Miriam, I believe. And before we go into detail on anything else, this is my LinkedIn. Professor Bodaway will probably have my email, my SJSU email, jonathan.austin@sjsu.edu. And then my personal email is also here because in my LinkedIn, obviously I'm showing you, because my school email will probably be deactivated after a certain amount of time. So in case it is, this is how you can reach me if you have any questions or something. But yeah, to just kind of hop into a general overview, which is what this presentation gives, very similarly organized to the report I showed you a little bit ago. But we're going to go ahead and skip to the embedded systems portion. This is a high-level block diagram of the system, but yeah, here. So, like I mentioned before, embedded systems team mostly revolves mostly around the DSP controller, which is the thing that's kind of hard to see right here. It's blue, and this is a development kit that gets passed on from each project member once they get here and then once they leave. So I'll be passing mine on eventually. And essentially, what this DSP controller does is it runs the main code and sends out PWMs to our main converters over here. And it sends those PWMs to the structure called H bridges. So yeah, here's the DSP controller. Here's another inverter board. So going back here, this is the H bridge. As you can tell, it kind of makes an H right here. And something to keep in mind for the stuff that I'm about to explain is that UC is going to stand for ultracapacitor, and ultracapacitors were initially designed into at the very beginning when this project was first being researched and thought up by Professor Bodaway in his paper. But we kind of learned that they're just a little bit too complex to include at the moment, but ultimately they would want to be included down the line just because of the benefits that they offer. But compared to a battery, like for example, battery can hold a lot more charge, but it discharges a lot slower. Ultracapacitor is the opposite. It holds a lot less charge, but can discharge a lot faster. So ultimately, you want to have both advantages. But like I said, it's just a little bit too hard to implement right now. So how we kind of designed everything in our time on the project is we stuck with the figure A because it doesn't include the ultracapacitor or the switches required to make it functional. And then also minus the switch 5. And that's why you see here. You see your little table here where these switches in the H-bridge control the polarity of the output. So it's either going to be on, off, or going the opposite direction, giving a negative output voltage. So it's just going to change depending on what the system is demanding for each of these battery modules. So like I mentioned before, the first thing that I spent a lot of time on was the SOC sorting. And what we needed to do first in order to implement this included this algorithm, which you can find, like I said, in Bodaway's IEEE paper, Model Predictive Control, and it's near the bottom. So this algorithm utilizes a structure of matrices in order to organize all the PWM modules. So when we initially were trying to implement this into the main code, first thing we had to do, because we didn't have ultracapacitors at the moment, is that we excluded anything that had to do with ultracapacitors or utilize them. So that's why you see these little blocks out right here. So first step was essentially removing that, and then also writing some test code to just kind of try to prove the logic of this sorting algorithm. So that's what I did here. This is just Visual Studio, another text editor like Code Composer Studio. And created constants, for example, to be able to actually test things. It just utilizes a simple insertion sort. And then there's some other things here to actually create the matrices. This code is pretty heavily commented out, so if you follow it line by line, you can see the relation of, for example, the steps to Bodaway's paper. So just being able to read through this code will most likely give you a better understanding of how the algorithm works, because this is the algorithm that's currently or this is a rough skeleton of the algorithm that is implemented in the main code currently. But yeah, so I highly encourage you to just kind of read through this. There are like some, for example, like numbers that are just set to constants, so that way we can test it. Like for example, these, like constant number of switches, constant number of switching modules, and the number of required modules for whatever the system's demanding. So once you run the code, you get this in your output window, which kind of displays different instantiations of what's going on step by step, so that way we could check the logic before we implemented it into the main code. So in the first 4 rows, you have your switching, your switches, so switches 1 through 4. And you can see what they're currently set to be either on or off. And then the row below that with the 3-digit numbers, 2 and 3-digit numbers, are going to be your random state of charge. Like I said, these are randomly generated because we just need them to be a constant, so that way we're able to test the code. So obviously these are varying states of charge, and then along with each of their states of charge, of course, they have to have an index number to be able to keep track of them. So that way our matrices can stay organized. So like I said, this code just uses a simple insertion sort. Obviously, you could have a more sophisticated sorting algorithm. It doesn't really matter. But we just went with something that was simple, so we could test the logic. So ultimately, it will sort each of these modules along and make sure that all their indices stay with them. So obviously, 184 is the largest number, so it's going to be on the left. And then it goes down from there all the way down to 28, the smallest number. So the point of this is to increase the efficiency of how we utilize our batteries. Obviously, you're going to want to use, in order to try to balance everything, you're going to want to use the batteries that have the highest state of charge. So it would be the 184 and 183, because, like I said, all we have here is just a constant number of required modules. But obviously, this number can be updated in the main code. So moving on, once those things are sorted, then that's when you start actually changing the status of each of these switches depending on the state of charge. So like I said, we're going to take the 2 highest, then we're going to alter it based off of Bodaway's algorithm, and then plug in the new statuses of each of the switches back into the main matrix. So you can see it changed from 1100 to 0110 for both 184 and 183, which correspond to index 0 and 5. So then, obviously, in the test code, that doesn't really do anything, but when it's actually implemented into the main code on the DSP, this would change the switch statuses of the through the sent PWMs from the DSP. So we tested it in 2 cases, one being this first development kit, like I talked about before, where it has a more simplified green board attached to it, and then we just probed those with, you can probe them with any sort of logic analyzer you can find to be able to see the waveforms and the statuses of each of the PWMs. For my case, I used the Adalm 2000, which was something that they gave during the pandemic for remote learning. It was essentially all in one, voltmeter, power supply, logic analyzer, you can do a lot of things. So this is a different logic analyzer, but essentially does the same thing. So obviously at the top row, you're going to be able to see your PWM on for a lot longer of a time. So you can create that sinusoidal wave. And here is where we tested it in the lab. So on the left, you're going to see your before, and then on the right, you'll see your after PWM waveforms to create that sinusoidal wave. So here is going to be where you have your main code, and there are videos explaining this code in a lot more detail and a lot better understanding than I could. That is referred to here in the Guide for New Members by Tristan, Miriam, and Xavier. But yeah, so this is essentially where the skeleton code that I wrote was implemented. So SOC sort algorithm here. Sarika was the one that essentially adapted the skeleton of the code to actually be functional inside the DSP. So as you can see, obviously it's actually altering the PWM channels instead of just some representative matrices elements. And yeah, so if you want to see how this is implemented well, you could definitely go through it, and there are comments here to help you figure it out. And the last part that kind of the project that was worked on that kind of bled into, the SOC sorting code and development, because obviously we didn't get it right the first time, bled into the second semester. But then what I kind of started with a little bit later was looking into actually how the SOC is estimated, because currently in the main code, it is just randomly generated. It's a random number. But ultimately, obviously, we want to get a real SOC when the project is more far along. So the question is, how do we get that? And that's kind of the work that I pointed out earlier of SAMS with the common filter. And essentially all the common filter is a linear estimation algorithm. But before I get into that, here is the simple model that I was talking about with Miriam's work that kind of shows and demonstrates the main functionality of majority of the control system here. You can see the parallels here that I drew with the colors. And here, for example, is the SOC that we're talking about that we ultimately want to estimate. But keep in mind, remember, we're only utilizing battery SOC at the moment because there's no ultracapacitors to do that for. And then right above that is just current, which would be sensed. So here's the common filter that I was talking about. So in order to actually try to simulate this in MATLAB, which is what Sam did, you need some sort of data for input current and output voltage. So the way he did this, to model like a battery cell, for example, is a couple of an RC network of resistor and then another resistor in parallel with a capacitor. And then it would take this data, which was generated out to an Excel sheet, which you'll find in his files. Then it uses that input current and output voltage to ultimately start trying to predict SOC for our code and system. So the first stage is going to be where you try to predict based off of the battery model, and then that estimate's going to get put back into there and then fed back into the beginning to adjust. So something that I kind of looked on besides trying to just understand this was how trying to figure out how to implement this into the main code, kind of like how Sarika and I did with the SOC sorting. But now we want to do this with an additional functionality of no longer having to generate those random SOC values, but get real SOC values. And this was made possible by the current sense module that Hiromi and Andrew helped develop, because like I said, we need real input current. We can't just rely on an LT spice model. We need the live feed. But yeah, so this is what the potential future work would be to adapt the common filter model into C code for implementation into the main code. So I've included a couple resources here at the very end after explaining some of the common filter, kind of just what I went over, with a link, which kind of has a simplified version of the common filter, and then also how to generate some C code from a MATLAB for a MATLAB common filtering algorithm. So this could be a good starting place for this, trying to develop this in a C code, but definitely, try to understand the common filter first through whatever means you have, of whether it's Sam's prior work or Bodaway's paper. And I believe Sam had some other online resources that maybe you could reach out to him about or ask Bodaway about. But yeah, in terms of going back to the SOC sorting algorithm, like I said, I did a lot of the skeleton code, and Sarika did a lot of the heavy lifting in trying to implement it into the main system. So if you want to see that implementation or further report stuff, just navigate your way to her individual folder, where you can see some more of the thought process behind it, of how it was thought up. Like here's my version 1. But then this is ultimately how it started getting implemented. So if you want more detail on that, like if it needs to be improved down the line, that's where you should go. But definitely there's a lot of future work potential with the common filter, like I mentioned before. And like I mentioned before, this project is definitely very complex. So you're going to come with like a lot of questions for a while, pretty much be asking questions the entire time. And you'll understand things slowly better and better. But if you do have any questions, don't hesitate to reach out to me. Just make sure to leave a note if you're trying to connect. That way I know what you're asking about. But yeah, once again, definitely a very interesting and complex project. Thank you, Professor Bodaway, for all your resources. And to you, whoever you are, enjoy seeing your project. And just go out and learn a lot. Thanks.